All right, as promised, I want to just take you through some practice problems dealing with logarithms. So we're going to take a look at these right now, and this is just writing these exponential forms into logarithmic form. We did some of those on the last video, but if you're wanting some more practice with different numbers here, we can do that as well. This first one says that we've got 9 squared equals 81. The base here is 9, so my logarithm has to have a base of 9 as well. And remember, a logarithm is what? It's an exponent. So it must equal the exponent there too. And this 81 is the input. Remember, because they're inverses to exponential functions, the output here is going to equal the input over here. So the log base 9 of 81 is equal to 2. Why? Because 9 raised to the power of 2 equals 81. Let's look at number 2. On number 2, I've got a base of 1/4. So my logarithm is going to have a base of 1/4, and it is raised to this power 3, and 1 over 64 is going to be my power there. Remember, let's see here, let's grab a scrap piece of paper. I want you to think about how this is calculated out. We've got 1 to the 4th cubed. That's the same thing as saying 1 cubed over 4 cubed, and that does equal 1 over 64. So when I take that 1/4 and I slide it over, I'm saying 1/4 cubed must equal 1 over 64, and it does. All right, let's look at the next one. It has a base of 8, and we're going to say, all right, so my logarithm must have a base of 8, log base 8. This is my exponent right here, 3, so it must equal 3 again. And so my input was the output on the exponential, 512. So log base 8 of 512 equals 3 is how we read that solution. Next one, we've got a base of 1/3, so my logarithm, oh, that's a horrible marker, I'm not going to use that one. My logarithm, just throw that away. My logarithm is going to be base 1/3, and it is of 9. That must equal the exponent -2. Think about what that means. That means if I take the 1/3 and I raise it to the power of -2, that should equal 9. Well, 1/3 raised to the power of -2 is the same thing as 1 to the -2 over 3 to the -2. And remember what that negative does. That negative sends this man right here up to the numerator, 3 squared, and it sends this guy right here down to the denominator. It's going to be 1 squared there, which I get 9 over 1, which equals 9. All right? So that's writing each in logarithmic form. Now I'm going to take a look at just evaluating some logarithms. So this says evaluate each logarithm. And we've got 5 problems here to go through. This one, we've got 2 raised to something. Remember, we can write an x here if we want to, and that would be 2 raised to the power of x is equal to 128. Now, you may not know right off the top of your head, 128 is 2 raised to what power? So what do we do here? We're going to take 128 and see if we can write it in base 2. So base 2 raised to some exponent and see what that exponent is. How do we get there? We need to factor out 128. So factoring out 128 is going to take a little bit more room here. So I'm going to pull up another scrap piece of paper. I'm going to say, okay, I've got 128. That's the same thing as 2 times 64. 64 is the same thing as 2 times 32, 2 times 16, 2 times 8, 2 times 4, and then 2 times 2. So how many 2's do I have there? I've got 1, 2, 3, 4, 5, 6, 7. Just count those again. 3, 6, 7. So this thing right here is the same thing as 2 to the 7th power. This is 2 to the x power. Since we've got the bases are the same, they're equal to one another, the exponents must be equal to one another, so x in this case is equal to 7. All right, let's take a look at this one. This is the log base 4 of 32. Once again, we can write this as equal to x. I'm going to switch pen colors so these don't run into one another, the last problem in this one. So this equals x. So 4 to the x is equal to 32. And I want to write these so that they are the same base. So if I take this 32, I can break it up into 2 times 16. 16 is 4 times 4. And each 4 breaks up into 2 times 2. And so how many 2's do I have there? I've got a total of 5 2's. So 32 is the same thing as 2 to the 5th power. Now 4x is not the same base as 2 to the 5th. That's base 4, that's base 2. I'm going to rewrite this 4 as 2 squared. And it's 2 squared raised to the x power. When I multiply these two right here, I get 2 to the 2x. And so 2 to the 2x is equal to 2 to the 5th. Since the bases are the same, I can set the exponents equal to one another. So 2x equals 5. Keep in mind, I'm not canceling anything out here. I'm just using what we call the one-to-one property. The bases are the same, so we can set the exponents to equal to each other. Solving for x, I get x equals 5 halves. Number 3. Number 3 says the log base 9 of 27. Let's let that equal x. And so 9 raised to the power of x must equal 27. Once again, these are not the same bases. Let's see if we can get them there. I know that 9 can be rewritten as 3 squared. So that's what I'm going to start with first. 9 is 3 squared, and that's being raised to the power of x. So I get 3 to the 2x. Now it is possible sometimes we'll have a number here that could be 9 raised to a power. I guess you could start with that number. But 27 is not a power of 9, is it? 27 breaks down to 3 times 9, and 9 breaks down to 3 times 3. So 27 is the same thing as 3 cubed. 9x is the same thing as 3 to the 2x. I've got these two things equal to one another. They are the same bases, so I can set the exponents equal to one another. And 2x is equal to 3. Solving for x, I get x equals 3 halves. So x is equal to 3 halves in this case. All right, let's look at the log base 2 of negative 32. Set that equal to x. So 2 raised to the power of x must equal negative 32. And let me find another scrap piece of paper. These are taking up more room than I anticipated. Sometimes I just start writing, and I get fairly large with my numbers there, or my work. So I'm going to break up 32, and hopefully we can get it down to a power of 2. This is 2 times 16. Well, we got to have a negative in here, don't we? So 2 times, negative 2 times, I'll just throw a negative right there for right now. 16 breaks up into 2 times 8. 8 breaks up into 2 times 4, and then we get 2 times 2. So 1, 2, 3, 4, 5 of these 2's. So I've got 5, 2 to the 2 to the 5th, and this is negative here. And if you think about it, if I got negative 2 times negative 2 times negative 2 times negative 2 times a negative 2, I've got an odd number of negatives here, so my answer will be negative. So I can write it like that, and it's the exact same thing. So this is 2 to the x is equal to negative 2 to the 5th power. Now, these bases are not the same because one is positive and one is negative. And with this, so let's see here. There's nothing I can really do here. If I make the exponent negative, that's going to make it go to the denominator, so it'd be 1 over 2 to the something. So that's not the solution here. Some students want to do that in this case. We can't make the exponent negative. We did break this up, but these are not the same base. They're super close, and it's really annoying because you're like, it's so close. Shouldn't I just say x is equal to 5? You can't do that. So I want to return to the problem here. And if you knew something about logarithms, and maybe you did, we can't take the log of a negative number. So this kind of goes back to when we talk about domains of functions. A logarithm is a function, and it has a domain as well. Let's take a look at the graph of log base 2 here. So if we switch over to Desmos, we can go ahead and start graphing here. If it opens up. There we go, I got it going. So we want to put in here log base 2 of x, all right? So if I type in log base, or just log of x, that's actually just log base 10, right? Because I didn't specifically tell it I want base 2. So I need to go through and put in log base 2. So if you go to functions, underneath here we've got miscellaneous, and then this right here is where you have log base of something. And notice we can type that in, log base 2. Get rid of that other log we put in. And now this is log base 2 of x. Now I want you to keep in mind something here. The x is our input. So this value right here at 2, for instance, when you put a 2 right here in for x, the value of 2 is 1. Let's take a look and appreciate that for a moment on a piece of paper. The log base 2 of 2. So if I have the log base 2 of 2, and I said evaluate that, what does that equal? Well, we'll just call it an x. You say, okay, I've got the 2 right here raised to this power, and that must equal this right here. So what value of x can I raise, what can I raise 2 to get the value to? 2 raised to what exponent equals 2? And x must equal 1 in this case. X is probably a bad usage here. Let's call it y. Y must equal 1. And so when we switch back to over here, it makes sense that if you put 2 in right here, our output must be 1, because the base 2 raised to the first power equals 2 itself, our input. And now the question becomes, well, what about negative 32? What happens when I put negative 32 in? Notice we have a vertical asymptote at x equals 0. There are no negative numbers here. So that's telling me that there's nothing, I can't put negative numbers into logarithms. It's not part of the domain of the function, because I can't raise any value to an exponent and get a negative number for my output. All right? So when you see you're taking the logarithm of a negative number, you should say, I got a domain error here. Just like when you take the square root of a negative number, notice this is not too much different than square root of x as far as domains go. There's your square root of x, and you can take the square root of 0. You actually can't even take the square root of a logarithm. So if I put 0 in here, notice it's going to give me undefined there as well. So there is a difference between the two. You can take the square root of 0, you get 0 as your answer. You can't take the logarithm of 0, and it goes back to the same reasonings here. I can't take 2 and raise it to some power and get 0 as my answer. For instance, suppose you had the log base 5 of 0 here. You say, okay, let that equal y. That means 5 raised to the y must equal 0. And what do you put in for y here that's going to make this equal to 0? If you put in 1, that equals 5. And if you put in 0, you get 1. There's nothing here that I can put in for y that's going to give me 0. Therefore, I can't put 0 into this function and get an actual exponent that would make this work. And so that's why we can't take the logarithm of 0, and for the same reason, we can't take the logarithm of negative numbers, because there's nothing that I can put in for y here that would give me, say, a negative 5. Nothing works there. There's no value that gives me negative 5 as my output. And therefore, inside of here, I can't take the logarithm of 0. I can't take the logarithm of negatives. I think you get the point. If not, talk to me. I know you're probably tired of me going on and on about it. Let's take a look at number 5 here. Number 5 says, find the log base 7, that's base 7 there, of 7 raised to the 6th power. So let's take a look at that one. If I write it in exponential form, it's got to have the same base 7. And we can go ahead and call this x right here. So I'm going to say 7, if you're converting it, slide it over. 7 raised to the x must equal 7 to the 6. So 7 raised to the x must equal 7 raised to the 6th power. Look at how nice that is. X must equal 6 there. So don't get confused by all of the base and then raised to another exponent. This actually makes it super easy for me. It becomes x to the 6th power. All right, so we've done a little bit of going from exponential form to logarithmic form, and we've done some going through logarithmic form to exponential form to solve them. Sometimes I might ask you to just say, hey, here's the logarithmic form, put it in exponential form for me. So this is maybe even a little bit easier than solving them, and that's what I want to just take you through a few practice problems looking at that. So this says, here's the logarithmic form, write it in exponential form. We know that the base of the exponent must be the same as the base of our logarithm here. And so I'm going to write 4 raised to the exponent of 4 must equal 256. That's the exponential form there. On the next one, we've got log base 7 of 1 equals 0. 7 is my base for my exponent also. It's raised to the exponent of 0, and that must equal 1. That makes sense. 7 raised to the 0 equals 1, right? For number 3, remember, if you have log with nothing written there, this is our common logarithm. That is a base 10. So our exponential form must have a base of 10. It's raised to that exponent, 1, and that equals 10. For the log base 5 of 5, I know that I must have in exponential form the same base, which is 5 right there. There's my exponent 1, and that equals 5 right here. And lastly, for this one right here, we've got a base of 12, so my exponential form must have a base of 12 also. It's raised to this negative exponent of negative 2, and that does equal 1 over 144. If you don't believe me, remember, raised to the negative 2 means to drop it down below, so you get 1 over 12 squared, and 1 over 12 squared does equal 1 over 144. So that's taking each one and writing it in exponential form. The next thing I want to talk to you about is a little bit of graphing with logarithms. So getting it used to here, first transformations. It follows the same transformation rules we learned about in chapter 1 of this class. And so I've got something like, let's see here, y equals log base 3 of x minus 2. This x minus 2 is paired with the x. So it's going to move in the opposite direction. This is going to be rightward 2. And that's kind of like when we had something like, let's suppose, go back to the basic parent function of x squared. If I had x minus 2 quantity squared, that's the parent function x squared, and we are moving it to the right 2. If I had x squared minus 2 on the outside, that is the parent function x squared, and then we're moving it down 2. So this is to the right 2, this is down 2, and that's what we've got going on with number 1 and 2 here. This one I didn't wrap it in parentheses, did I? So I'm saying take the log base 3 of x and then subtract 2 from your value. So this minus 2, because it's not grouped with the x, means to move it downward 2. Be very careful. Notice how close those look, but they're very much different. One moves it to the right 2, one moves it down 2. Notice the directions also said to identify the parent function. Now logarithms, unlike something like x squared where you've got this is the parent function, logarithms have a lot of different parent functions, and it all depends on what the base is. So log base 3 of x is the parent function for these. The next one is log base 6. Log base 6 is a totally different parent function from log base 3. They're not transformations of one another. They've got their own parent functions. So there's an infinite amount of logarithms, parent functions there, and it all depends on the base. So that's why a lot of times you'll see the transformation written out as log base b, and then you apply your transformations to them. So this one right here, the parent function is log base 6. This plus 1 is going to move it left 1. Left positive 1, and we'll just say left 1. There we go, that makes more sense. And then the negative 5 here moves it downward 5. So if you can graph the parent function log base 6, then you know to shift all the points over to the left 1 and then shift them all down 5. Same thing with this one. This is log base 2. That's our parent function. we're going to shift it to the right. Remember, it moves opposite what feels natural there. Because it's paired with the x, it moves right 4. And then this one right here tells us to move it up 1. So those same transformations we learned with other parent functions apply to logarithms here as well. Now, to finish out this video, I want to take you through 2 examples of graphing logarithms. We're going to use kind of like an inverse technique to help us graph those. This one right here says to graph the log base 10 of x. Remember, nothing's written there. It's our common logarithm with a base of 10. So as you go through and you're trying to come up with points to graph this, I think it's very helpful a lot of times when we're graphing logarithms to think about the exponential function. So if I'm thinking, if I make a chart here for 10 to the x, because remember that is the inverse of log base 10 of x. This is my chart here. This is my x and my y. I'm going to put in a few values like -2, -1, 0, 1, and 2. So when x is equal to -2, y's value here is 10 to the -2, which is the same thing as 1 over 100. When x is -1, I get 1 over 10. When x is 0, I get 1. When x is 1, I get 10. And when x is 2, I get 100. So if I'm graphing this, this is the exponential function I'm graphing, by the way. When I'm graphing this, I'm going to plot these points if you don't know them. So I've got 0, 1. That's where it crosses the y-axis. 1, 10, 1, 2, 3, 4, 5, 6, 7, 8. It's way up there somewhere. That's not the actual points, up a little bit higher. And then at -1, I'm at 1/10. At -2, I'm really close to the x-axis, and so this thing almost touches the x-axis, but it never does, and then it shoots up pretty steeply very quickly, right? And so this is 10 raised to the power of x. Now the inverse to this is log base 10 of x, and it should look like it's being reflected over y equals x. So that's how I'm going to use this to graph the inverse, or log base 10 of x. I'm going to switch my x and y, because that's what inverses do, right? You can switch that chart. So we have log of x here. And so what was y is going to become my x's. So I have 1 over 100, 1 over 10, 1, 10, and 100. So I took my y's and put them in for x's because they're inverses, and the output should be the same as the x's over here. So we've got -2, -1, 0, 1, and 2. And that's what I'm going to graph right here. So when x is 1 over 100, really close to the y-axis, my y value is -2. When x is 1 over 10, which is even harder to graph here than because I already got 1/100th is right there, I'm going to have -1. So with this marker, it's almost impossible to show a difference between that. At x equals 1, I've got 0, so that's where it crosses. And then I've got 10, 1, which is going to be out here. And so this is going to look like this right here. And notice if I put these two together, they should look like we're reflecting over y equals x, that diagonal line coming through like this. So when I'm asking you to graph something like this, I'm wanting you to show that there's a vertical asymptote here. It never does reach 0 as far as an x value goes. Our domain should be anything bigger than 0. And I'm really looking for that crossing point right there. And we talked about that in another video. With exponential functions, they cross right here at 0, 1. With logarithmic ones, if there's no transformations, it's going to be crossing at 1, 0. So there's our graph of log base 10 of x, or our common logarithm. The next one is going to look like this right here. That's what I want you to graph. The log base 3 of x plus 5. So pause the video and give that one a try. All right, I've taken it that you've given that one a try. Maybe used one way to graph it, maybe used another. Let's take and see how you can do this. This one right here, there's two ways. That's why I say maybe use one, maybe use the other. You could graph log base 3 of x. using the same technique we did for log base 10 of x, and then shift everything to the left 5 because you recognize, hey, there's a transformation there. The other thing you could do is actually solve for the inverse to this and then graph that. So what I want to do is first just look at it from a transformation approach. I want to say log base 3 of x. If I just think about that, what does that look like graphed? Well, first I need to find what is the inverse 3 to the x. What's its x and y chart look like? So this is for the function 3 to the x, and then I'm going to make a chart for this one right here. So let's put in a few values like -2, -1, 0, 1, and 2. 3 to the -2 is 1/9. 3 to the -1 is 1/3. Then 1. Then we have 3. Then we have 9. Now if I switch those, I come up with an xy chart for log base 3 of x. So 1/9, 1/3, 1, 3, and 9. And then I get -2, -1, 0, 1, 2. Now, keep in mind I'm graphing log base 3 of x, which is different than log base 3 of x plus 5. So 1/9 I get -2. At 1/3 I'm at -1. At 1 I'm at 0. 3 I'm at 1. And then at 9 I'm at 2. So 1, 2, 3, 4, 5, 6, 7, 8. I need to make these a little bit larger. So it's about right there as we go through. And so graphing this is just log base 3 of x. If I want to graph log base 3 of x plus 5, I need to shift all these points to the left 5. So here's where we have a case where we're going to move into the negative realm. And so let's see, my x values are going to move over by 5. So it's going to be 1/9 minus 5 here. And so right now my vertical asymptote is at x equals 0. If I shift that over to the left 5, I'm going to be at 1, 2, 3, 4, 5. Right here's the vertical asymptote. And now basically I'm going to graph the same thing and just kind of pretend like this is the y-axis. So I've got a point right here. Here, this is like that special point I want to make sure that you graph because it moved over 5 spaces. It was at 1, 0. Now it's at -4, 0. And then I'm going to go over 2 from it and up 1. And now I can graph that point where we're 9 away from that vertical asymptote. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're at 2. And so there it is, shift it to the left 5. This is what I want you to graph, the log base 3 of x plus 5. So that's one way you can do it there, all right? But there's another way. I'm going to show you how to do it without graphing and doing the transformation, and that is doing this. We're going to take this right here, and we're going to find the inverse to it. And how do we do that? Well, the same technique that we used back in Chapter 1 for finding inverses of functions. We're going to write down our function. Boom, it's already written down for me there. And I'm going to switch the x and y and solve. So if I switch x and y, I get x equals the log base 3 of y plus 5. And then I'm going to get y by itself. So how do I do that? Write it in exponential form. So this is 3 raised to the power of x, and that equals y plus 5. So 3 raised to this power equals that right there. Subtract 5 from both sides, and I get 3 to the x minus 5 is equal to y. This is the inverse function to log base 3 of x plus 5. So if I write out a chart, an xy chart for that there, then I can switch the x and y's and graph the result. So let's do that. Once again, I'm going to use those points. So let's make an xy chart for this graph right here. -2, -1, 0, 1, and 2. And putting that in, I get 1/9 minus 5. And then I get 1/3 minus 5. That's a pain to do, isn't it? And then we get 0 minus 5, which is -5. 1 minus 5, which is -4. Not 1 minus 5. 3 minus 5. 1 right there. I'm moving too fast here. 3 minus 5 is -2. And then 3 squared is 9 minus 5 is 4. So this is my xy chart here. I do need to probably work these fractions out. So I'm going to pause the video and do that just so I don't take up too much of your time. All right, so just so you could see it, when I put in 1/9 minus 5, you can pause if you want to look at my work. I just didn't want to bother you with all the math there. We got negative 4.9. That's your y value. And then same thing, when 1/3 minus 5 over 1, doing the fractional work there, I got negative 4.6. And I just say that because we're trying to graph the points. It makes it a little bit easier if we write it out like that. So this is the exponential function that is the inverse to that logarithm. This is an XY chart for a few values to it. So now what I'm going to do is say, okay, what is my XY chart for the log base 3 of y plus 5 using these values and just switching the x and y's. So I have negative 4.9 comma negative 2. Then I'm going to get negative 4.6 comma negative 1, negative 5 comma 0, negative 2 comma 1, and then 4 comma 2. And I just realized I made another mistake over here. Boy, I'm just full of them today, aren't I? So if you put 0 in for x, you're going to get 1, and 1 minus 5 is negative 4. So that should be negative 4 right there, which makes this one right here negative 4. Hopefully, no more mistakes are in there. We'll find out when we go to graph this thing, though. So as I'm graphing it, I'm just going to plot these points and graph. So I've got negative 4.9 comma negative 2. 1, 2, 3, 4.9, negative 2 right here. And then I've got negative 4.6 just a little bit further over, and I'm at negative 1. And then at negative 4, we're at 0. See, I would have realized right here I made that mistake if I was graphing. I'd been like, how do I go to negative 5, 0? Because I know what the shape should look like. Negative 2, 1. And then 4, 2. And so our graph is going to look like this coming through right here. And we can see that we're going to have that vertical asymptote coming like this right here. So this also should be the log base 3 of y plus 5. Compare it to the one we just did using transformations, and they are spot on with one another. All right? That's two different ways that you can do that problem right there. All right, I don't care which way you use. I think the inverse method will probably be more consistent for you because we won't always recognize the transformation. So if you find the inverse, you can make your XY chart, and then you can switch those around and graph your logarithms. We won't do a whole lot of graphing logarithms in here, but for the basic ones, it's not a bad skill to have because we start to see characteristics with the domain and the range that otherwise we might forget about if we didn't practice graphing them some. Okay? Let me know if you have any questions with logarithms. I'd be happy to help you. Thank you for watching. Have a good day.